Scientists had discovered the deepest part of the ocean. It is the lowest known point on the planet.
To get a sense of just how deep trenches are, take the height of Mount Everest, we would still have about a mile of water above us.
The deepest place on Earth just spoke, and AI understood it. For decades, the Mariana Trench was a silent scar in the Pacific, a world so dark and crushing that even sunlight gives up. Then, an AI scan sliced through the noise and pulled out patterns no human ear could trace, exposing sounds and life few dared imagine.
Nobody thought the ocean was this deep, so all of a sudden we've got scientists saying, why is that?
Just before we landed, we saw a flatfish about a foot long, and that's a bottom-dwelling fish, so if you see one, there are others.
What if the quiet abyss isn't quiet at all? What if familiar species act in unfamiliar ways? And what if the most remote place on Earth already bears our fingerprints? This is not a rumor. It's a revelation and a warning. AI maps the abyss. For centuries, the Mariana Trench has stood as the ultimate symbol of mystery on Earth. Many imagine it as a single vertical shaft plunging into eternal night. But in reality, it is a sprawling, jagged labyrinth. Stretching for over 1,500 miles, it resembles a scar carved into the ocean floor by the relentless motion of tectonic plates. Its deepest point, Challenger Deep, sinks nearly 11 kilometers beneath the surface. To put that into perspective, if Mount Everest were placed inside, its summit would still be more than a mile underwater. Down there, pressures soar to over 1,000 times what we feel at sea level. The weight is so immense that even the strongest steel can buckle, and electronics that work flawlessly on the surface often fail within minutes. These conditions make the trench less explored than Mars, a region so hostile that even our best machines often return with corrupted readings, broken instruments, or incomplete maps. Traditional tools for exploration, sonar, hydrophones, submersibles, have always been hampered by these extremes. Sonar beams scatter and distort under shifting thermoclines. Long-term hydrophone surveys pick up endless static, the roar of distant earthquakes, the grumble of shifting tectonic plates, and the faint calls of creatures migrating through the Pacific. To human analysts, this avalanche of data is nearly impenetrable. Sorting it manually would take lifetimes, with no guarantee of finding what truly matters. For decades, much of what was recorded from the trench was filed away in archives, a mountain of sound that no one had the capacity to truly unravel. Artificial intelligence changed that equation. Instead of relying on human ears and biased guesses, machine learning approaches the trench with no assumptions. By processing hundreds of thousands of hours of recordings, AI systems separate chaos from structure. What once sounded like endless background noise, pops, hums, and echoes suddenly becomes a catalog of repeatable signatures. Each sound is stripped down, measured, and compared across time and location, building a searchable library of the deep. This is not just sound recognition, but pattern analysis at a scale that humans cannot achieve. Imagine trying to identify a single bird call in the middle of a thunderstorm. Now imagine doing it across every thunderstorm recorded for an entire decade. That is what AI brought to the abyss. The breakthrough came not only from its ability to hear, but to correlate. AI systems were designed to cross-reference detections with other databases, weather records, seismic activity, and, most importantly, sightings of marine life. For example, when whales were observed near the trench at specific times, AI could check whether unusual sounds were also present. Over years of data, these correlations became too strong to dismiss as chance. What once looked like isolated anomalies began to form coherent patterns. A sound repeated during winter migrations, another clustered around seamounts, another during periods of unusual ocean warming. These weren't random hisses. They were voices, signals hidden in the static. The implications are staggering. With AI, scientists can test hypotheses at scale. Instead of asking, "Could this sound belong to a whale?" they can ask, "Does this sound appear every time whales pass through these waters?" Instead of guessing at geological rumbles, they can model whether the tremors match known fault lines. Each successful correlation pushes the confidence needle from speculation towards certainty. The trench, once a void of mystery, is slowly becoming legible. The first pattern the AI dragged from the black wasn't a quake, a vent, or a ship. It was a voice unlike anything on record. The Biot twang mystery. In 2014, during what should have been a routine acoustic survey of the Western Pacific, researchers stumbled across a sound that defied every expectation. The recording lasted only a few seconds, between 2.5 and 3.5 seconds to be exact. But in that short window, it packed more complexity than anything they had ever captured in these depths. It began as a deep, resonant moan, like the low note of a distant organ echoing through water. Then it shifted, stepping through a series of mid-range tones before ending with a piercing metallic twang that reached nearly 8,000 hertz. The strange part wasn't just its odd shape. It was its structure. Unlike random geological noise or the chaotic bursts of seismic rumbles, this signal carried distinct parts: a beginning, middle, and end. It sounded composed, almost intentional. Scientists listening to the playback knew instantly that this was not the dull roar of undersea quakes or the groan of tectonic plates grinding together. Nature has its rhythms, but this was different. It had the cadence of a voice, segmented in a way that suggested communication. The researchers nicknamed it the Biot twang, a label that captured both its organic undertone and the bizarre, futuristic twang at its peak. It was as if the ocean itself had spoken in a language no one could decipher. The real shock came when the sound reappeared. It wasn't a one-off anomaly, the kind of glitch that could be shrugged off as faulty equipment. Instead, the Biot twang echoed again and again, recorded at multiple stations spread across the Western Pacific. The calls persisted for months, cropping up in different seasons, in varied conditions, and at different depths. Yet, when scientists compared notes, no ship logs reported unusual marine activity in the area at the time of the recordings. No underwater cameras captured a creature making the noise, and no known library of ocean calls, compiled from decades of whale songs, dolphin clicks, and other marine vocalizations, contained anything that matched. This left researchers circling through a dizzying range of theories. Some believed it might come from a new species, one yet to be documented by science, perhaps an elusive giant that roamed the twilight zones of the Pacific. Others thought the culprit might not be biological at all. Could extreme geological forces under immense pressure produce sound in a way never before recorded? The structure argued against it, but the trench is a place where even geology behaves differently. A smaller camp clung to the possibility of faulty instruments. Yet, the consistent repetition across different platforms and times undermined that explanation. A broken microphone doesn't repeat the same sequence across months and miles of ocean. The comparisons with known species only deepened the mystery. Early analyses showed similarities with baleen whales, particularly minke and Briday's whales. But the match was never perfect. Baleen whale calls often unfold in long, low-frequency songs, sometimes lasting minutes. The Biot twang, with its brief 5-part arc and metallic finish, seemed like a cousin, not a sibling. If it was a whale, it was doing something no whale on record had ever done before. Theories multiplied. Was it a mating call, designed to stand out in a soundscape of overlapping songs? Was it a navigation tool, A sonar-like beacon unique to the deep trenches? Or was it something stranger still, an acoustic behavior evolved to survive in an environment beyond our reach? The enigma lingered for years, frustrating experts and sparking speculation outside scientific circles. Some journalists framed it as the ocean's alien signal, while others drew parallels to science fiction sound effects, likening it to the hum of a starship engine or the pulse of extraterrestrial technology. The more it defied categorization, the more the Biot twang captured public imagination. Yet beneath the hype, serious scientists pressed on, unwilling to settle for rumor. They knew that somewhere inside the layers of static and mystery, the truth was waiting. But they also knew that human analysis alone might never be enough. That's when artificial intelligence entered the stage. The recordings were already in storage, countless hours of audio that humans had only scratched at. The question became clear. Could AI find the missing link? Could it correlate the biotwang not just with sound spectrograms, but with living, breathing animals seen in the trench? Then came the hard test. Could AI link the sound to a living culprit, not just a curve on a spectrogram? Deeper than Mars, when people talk about frontiers, their minds often leap to space, the red plains of Mars, the icy moons of Jupiter, or the endless stars overhead. Yet the greatest unexplored wilderness may not be above us at all, but below. Despite billions invested in planetary probes, fewer than a few dozen human beings have ever reached the bottom of Challenger Deep, the Mariana Trench's deepest point. By contrast, Mars has hosted fleets of orbiters, rovers, and landers. Entire landscapes of another world have been mapped in detail, while the abyss on our own planet remains a shadow on sonar charts. It is almost paradoxical. In some ways, we know more about a distant desert planet than the trench lying 7 miles beneath the Pacific. The reason is simple. The abyss is harsher than Mars in ways we seldom imagine. Down there, the pressure exceeds 1,000 atmospheres, enough to crush a steel-hulled submarine like a soda can. Temperatures hover just above freezing year-round, sapping heat from every surface. Sunlight never touches the bottom, leaving it in perpetual night. Electronics that work flawlessly in space often fail within minutes under these conditions. Wires seize, batteries collapse, casings fracture. Even communication itself becomes a challenge. Signals crawl through water at a fraction of the speed they move through space, making real-time control nearly impossible. Sending a rover to Mars might be costly, but sending a robot to Challenger Deep can feel like a gamble, where the ocean itself conspires to erase your technology. Yet, despite the cruelty of the environment, life persists. What makes survival possible in such a barren place? The answer is almost poetic. Crumbs. Scientists call it marine snow, a gentle, continuous rain of dead plankton, fish scales, tiny shells, and fragments of organic matter drifting down from the sunlit layers above. To the creatures of the trench, these fragments are gold dust, the only currency of survival. But the supply is painfully thin. Every organism is forced into razor-edged efficiency, eking out existence from scarcity. Oxygen is scarce, food is almost absent, and mistakes mean extinction. To thrive here requires evolutionary tricks unlike anywhere else on Earth. Each adaptation, whether it's the ability to extract energy from the faintest chemical traces or the capacity to store oxygen for long dives, is pushed to the very limit. The geography of the trench amplifies these challenges. Far from being one smooth canyon, the trench is a maze of ridges, cliffs, and valleys. Each pocket becomes an island unto itself, cut off by crushing pressure and freezing dark. Within these isolated pockets, species can evolve in relative secrecy, adapting uniquely to their small domains. One valley may favor creatures with glowing organs that pierce the gloom. Another may harbor microbes that thrive on sulfur bubbling from unseen vents. The trench is less like a single ecosystem and more like a series of locked rooms, each with its own rules. For scientists, this makes the abyss a kind of black box, Earth's own vault of secrets, holding evolutionary experiments we may never see elsewhere. This fragmented isolation means that every descent into the trench carries the possibility of revelation. Unlike the open ocean, where species roam vast ranges, the trench fosters local adaptations, specialized behaviors, and perhaps creatures seen nowhere else. Each mission has the potential to uncover something entirely novel, whether in the form of an unfamiliar fish, a new strain of microbe, or a biological solution to pressure that might inspire human technology. But just as often, the trench greets explorers with silence. A silence so complete that it becomes oppressive. Hours of recordings may yield nothing but the sound of water and distant geological murmurs. And yet, even in this silence, there are voices waiting to be heard. The AI scans proved it. Buried in the static, hidden in the monotony, the machines pulled out something stunning. A repeating pattern, not noise, but song. It wasn't the groan of shifting tectonic plates or the whisper of marine snow falling through the dark. It was a chorus line, a call that belonged to a living creature. In this near silence, AI found a chorus line, and it finally put a name to the singer. Whale identity revealed. For nearly 2 years, the Biot twang lingered as a ghost in the data, a structured, repeating sound with no visible source. Theories multiplied, arguments grew heated, and yet the culprit refused to show itself. Then, artificial intelligence finally broke the deadlock. By cross-referencing thousands of hours of audio with detailed observation logs, AI began to reveal a pattern that no human analyst had been able to see clearly. Each time the unusual call appeared, observers in the field had reported sightings of Bride's whales in the same region. At first, the overlap seemed coincidental, but as the data pool expanded, the pattern repeated, once, twice, then 9 separate, independent matches. 9 times, the sound and the species appeared together. The odds of that happening by chance collapsed to nearly 0. The AI had drawn the connection. The Biot twang was no phantom. It was the voice of Bride's whales. For many scientists, the revelation was both exhilarating and puzzling. Bride's whales, medium-sized baleen giants, are not especially rare. They inhabit warm tropical and subtropical seas across the world. Their songs, moans, and calls have been recorded for decades. Yet, never before had a call like the Biot twang been linked to them. The discovery meant that these whales were producing an entirely new form of communication, one so unusual it had fooled experts into believing it might belong to a species unknown to science. That alone was enough to rewrite parts of marine biology. But the deeper implications lay in the structure of the call itself. Unlike the long, drawn-out moans of other baleen whales or the rhythmic songs of humpbacks, the Biot twang carried an odd 5-part structure. It began low, climbed through shifting midtones, then ended with a sharp, metallic twang that pierced the ocean at nearly 8 kilohertz. It was like a musical scale compressed into a single breath. Researchers began to speculate that this peculiar architecture might represent a regional dialect. Just as human languages develop accents shaped by geography, whales too may adopt unique sound patterns shaped by their environment. The Mariana Trench is no ordinary environment. Its extreme acoustics, where sound waves bend and refract through layers of cold, dense water, create one of the strangest soundscapes on Earth. Noise can travel for hundreds of miles, then vanish suddenly as if swallowed by the dark. In such a setting, having a call that stands out could be a matter of survival. The Biot twang may function as a contact signal, allowing bride's whales to locate one another across vast, empty distances where visibility is zero and the only constant is silence. Some researchers even described it as the ocean's version of Marco Polo, a call and response game to keep track of companions in a world without landmarks. Yet, if the mystery had been solved, new questions erupted in its place. Why this call here and not elsewhere? Were the whales adapting to the trench itself, modifying their communication to fit its strange acoustics? Or were they revealing a hidden behavioral repertoire that scientists had simply never noticed before? And how deep did bride's whales truly go? Officially, they are not classified as deep-diving species. But if their calls were being detected near the trench, did that mean they were pushing into depths previously thought beyond their reach? The geometry of the ocean complicates the answer. Sound can bend, amplify, or carry far from its source. Determining whether the whales were truly diving into the abyss or merely singing above it remains one of the unresolved riddles of the discovery. In the end, the AI had given scientists something precious: a culprit, a context, and a confirmation. But it had also reminded them that answers in the ocean are rarely neat. Every solved puzzle seems to split into a dozen new ones. The Biot twang, once a terrifying enigma, had become a familiar voice. Yet its strangeness lingered, hinting that even known species could harbor behaviors we barely understand. And while the giants sang their cryptic songs above, something even stranger stirred below. The mud of the trench concealed not just voices, but entire worlds, a biosphere we'd never catalogued. While giants sang above, the mud below held something far stranger, a biosphere we'd never catalogued. Alien microbial vault. When scientists drilled into the sediments of the Mariana Trench, they expected to find some microbial life. After all, bacteria and archaea are known to occupy even the harshest environments on Earth. But what the analysis revealed was nothing short of astonishing. Nearly 90% of the microbial species they identified had never been seen before. Out of every 10 organisms catalogued, 9 were entirely new to science. This wasn't a few strange outliers, it was an entire hidden biosphere. To confirm it, researchers sequenced more than 1,000 sediment samples and processed over 90 terabases of genetic data, one of the largest deep ocean surveys ever conducted. The picture that emerged was startling. The trench wasn't just another ecosystem. It was a microbial vault, sealed in pressure and darkness for millions of years, harboring life forms more alien than anything a telescope had shown us from space. These microbes thrive without a single ray of sunlight. Photosynthesis, the engine that powers nearly all surface ecosystems, has no place in their world. Instead, trench microbes draw energy from chemistry itself. Some tap the reactions of nitrogen, converting it into usable forms for other organisms. Others recycle sulfur, keeping the delicate balance of deep-sea systems in check. Still others extract energy directly from interactions between seawater and the Earth's crust. In doing so, they redefine what it means for life to exist. The trench demonstrates that biology doesn't need green leaves, chlorophyll, or even light. It can write its story with chemistry alone. That revelation stretches far beyond the Pacific. If microbes can live in pitch black, under crushing pressure, in near-freezing water, then perhaps life on icy moons like Europa or Enceladus is not only possible, but likely. Scientists have long speculated that extraterrestrial oceans could host biology, but the trench provides a proof of concept right here on Earth. It shows us that life can adapt to conditions once thought uninhabitable, rewriting the boundaries of possibility. The abyss is, in many ways, a stand-in for alien worlds. Only here, the aliens are microbes, and they're living under our oceans. The surprises didn't stop at discovery. When scientists studied how these organisms actually functioned, they realized the microbes carried extraordinary survival tools, enzymes, and proteins fine-tuned to endure extremes. Under normal pressure, proteins fold neatly into shapes that allow them to function. But under trench conditions, those same proteins should collapse. The microbes had evolved versions that resist such breakdown, remaining stable where most molecular machinery would shatter. Some enzymes also functioned efficiently at near-freezing temperatures, catalyzing reactions that would normally grind to a halt. Others contained antioxidant systems that neutralized cellular damage caused by stress. These traits are more than curiosities. They represent a kind of biotech treasure chest. Pressure-proof proteins could inspire industrial enzymes that work under harsh factory conditions. Cold active catalysts may lead to breakthroughs in medicine, food storage, or even biofuels. Antioxidant systems might unlock therapies to protect human cells from aging or disease. In other words, the trench doesn't just expand our imagination, it may hold keys to future technologies. The smallest organisms in the ocean's deepest place could end up transforming industries on the surface. But as with every discovery in the trench, each answer brought more questions. If microbes can survive here, how many more remain hidden in unstudied sediments? How long have they been isolated? And how much of their genetic code is unlike anything we've ever encountered? Most of all, what does it say about the resilience of life itself, that in the most crushing, frozen, lightless corner of Earth, existence not only persists but thrives? Scientists began to realize that while microbes offered the clearest look at survival in the abyss, they were not the only ones carrying evolutionary secrets. Beyond the sediments, larger animals showed adaptations just as profound. And when researchers compared them, a remarkable pattern emerged. Different species, separated by millions of years of evolution, were using the same tricks to survive. Zoom out from microbes to animals and a pattern appears. Evolution keeps choosing the same tricks. Convergent survival tricks. When biologists began comparing the adaptations of different creatures in the Mariana Trench, they expected to find wildly unique solutions. After all, the snailfish and the amphipod, the two most studied residents of the deep, sit on distant branches of the evolutionary tree. Snailfish are vertebrates, descendants of the same lineage that produced salmon and trout. Amphipods, on the other hand, are crustaceans, tiny armored scavengers closer to shrimp than to fish. With such different histories, one might assume their strategies for survival would be equally diverse. But the reality stunned scientists. Despite their unrelated ancestries, both groups had converged on the same molecular trick: TMAO-boosted chemistry. TMAO, or trimethylamine N-oxide, is a compound that stabilizes proteins under crushing pressure. Without it, the delicate folds that give proteins their function would collapse. Proteins would unravel like broken springs, enzymes would fail, and life itself would grind to a halt. Yet, in snailfish and amphipods alike, scientists discovered unusually high concentrations of TMAO. It acted like a universal scaffolding system, propping up the molecular machinery of cells so they could keep working, even when the ocean pressed down with the weight of mountains. This wasn't a coincidence. It was convergence. Nature finding the same answer twice in two very different bodies when confronted with the same problem. Other adaptations carried the same echoes. Snailfish had evolved soft bodies and fluid cell membranes. Instead of resisting pressure with rigid structures, they allowed themselves to bend and flex with it. Their tissues were almost gelatinous, their bones reduced, their design more like pliable clay than brittle glass. Amphipods, by contrast, built resilience into their very chemistry. Their cells produced antioxidant shields that protected against stress-induced damage. Specialized proteins gave their tissues a kind of inner armor, resisting collapse at depths that would eradicate most shallow water species. Different strategies on the surface, yet underneath, both followed the same script: preserve the core functions of life by adapting proteins, membranes, and defenses to withstand the abyss. What fascinated researchers most was not simply that these solutions worked, it was that they repeated, over and over, across species that had no recent common ancestor, the same answers emerged. This is the essence of convergent evolution. When environments push hard enough, life has only so many viable tricks, and it will find them again and again. Evolution, it seemed, was less of an open-ended improvisation and more of a piano with limited keys. Press down in the right place, crushing pressure, freezing dark, and the same notes will play, no matter which instrument you use. This realization didn't just rewrite how we see the trench, it reshaped how scientists think about life in the universe. If extreme environments on Earth force different species into the same solutions, then perhaps alien worlds will too. A frozen ocean under Europa's icy crust, or the methane seas of Titan, might not host beings utterly unlike us, but creatures that mirror deep-sea life in familiar ways. They too might rely on chemical stabilizers, flexible bodies, or stress-resistant proteins. Convergent evolution suggests that biology has rules, and those rules may be universal. Astrobiologists now see the trench as a cheat sheet, a manual for what to expect when searching for life beyond Earth. It's humbling to realize that the same laws that sculpted snailfish in the Pacific could shape something swimming beneath the ice of a distant moon. The Mariana Trench, once thought of as a forbidding pit of darkness, becomes instead a mirror, showing us not just how Earth's life survives, but how life itself might persist anywhere. But the trench holds a quieter pattern too, our signature, etched into everything that sinks. A warning from the deep. For generations, the Mariana Trench was imagined as a sanctuary beyond human reach, a place so remote and forbidding that our actions could never touch it. But when researchers sampled amphipods scuttling across the seafloor more than 11 kilometers down, the results shattered that illusion. Inside their tiny bodies, scientists detected PCBs and PBDES, toxic industrial chemicals banned decades ago for their destructive effects on health and ecosystems. Somehow, these substances had traveled from factory smokestacks and city drains to the most inaccessible corner of the planet. The carriers were depressingly ordinary: microplastics and marine snow. Bit by bit, fragments of waste drifted down through the water column, binding to organic debris, and carried the poisons into the trench's black depths. The abyss, once thought untouchable, had become Earth's ultimate sinkhole for pollution. The discovery was more than symbolic. It was alarming in scale. Tests showed that the contamination levels in some trench species weren't just detectable. They were comparable to, or even higher than, the levels found in animals living near industrial rivers and polluted coastlines. This was a revelation few had expected. If the most remote place on Earth could rival chemical hotspots at the heart of human activity, then nowhere on the planet could truly be called pristine. Far away had ceased to exist. Everything flows downhill eventually, and in the ocean, downhill means the trench. The consequences ripple outward in ways scientists are only beginning to chart. Once pollutants enter the trench food web, they don't stay neatly contained in amphipods. Small predators eat the contaminated crustaceans. Larger creatures eat them in turn. With each step up the ladder, the toxins biomagnify, accumulating in higher concentrations at each level. In a place where food is already scarce, every mouthful carries the risk of poisoning. This means that even creatures uniquely adapted to survive crushing pressure and freezing dark cannot escape the invisible hand of human industry. Their survival strategies, perfected over millions of years, may now be undone by a legacy of chemicals drifting down from the surface. And yet, amid the grimness, a new kind of tool offers hope. The same artificial intelligence that decoded whale songs is now being applied to the problem of pollution. By analyzing thousands of recordings and samples, AI can track the subtle pathways toxins follow, forecast hotspots where pollutants may accumulate, and even map the global circulation patterns that deliver our waste into the deepest trenches. In a sense, the abyss has become both archive and alarm. It holds the memory of everything we discard, and through AI, that memory can now be read. Every molecule of plastic, every banned chemical, every toxic ghost of industry writes itself into the trench's record. If this dive opened your eyes, like, comment, and subscribe. Tell us which revelation hit you hardest: the Biot twang decoded, the alien microbes, or the pollution no one can outrun. And when you're ready to go deeper, watch the next video on your screen. We're mapping the rest of Earth's hidden oceans, one signal at a time.